Hello everybody. I'm frustrated again because I did go through all of this, made another video, and I don't know why. Sometimes they don't save and sometimes they do. So now I have to do this all over again. But I'm not going to rewrite it all. I'm just going to show you the answers because I'm not going to go through it all again. But I will explain them to you. I'm just not going to write them all over again because I've already done it. Alright, so this is where we ended up with the last video. Alright, so here it says that, let's cover it up. How about that? Well, we'll cover it up for now. In the upper atmosphere, ozone molecules decompose with ultraviolet radiation. And here's the equation that they do that by. Alright, so a molecule of O3 absorbs a photon, just one, with a frequency of 1.0 times 10 to the 15th per second. Per second is the same thing as a hertz. I've always said hertz, but they use per second in AP. Alright, how much energy in joules does the O3 absorb? So you have these equations. They're not things you have to know. You just have to know how to use them. E is equal to h nu, and nu is frequency. So we're given the frequency, we're given the h, we know what, we can use the h. Just have to remember that when we do that, the answer is going to be in joules, because if you look at, excuse me, that is joule seconds. Alright, so that's joules, and that's joules per photon. Because it was one photon. This is one photon. So this is going to be joules per photon. Alright. The minimum energy needed to break that bond is 387 kilojoules per mole. Does your photon with this frequency have enough energy to break that bond? So this is how much energy, this is how many joules per photon it has. We need to know how many kilojoules per mole does that photon have. So what we're going to do is we're going to say, okay, that's how many joules there are per photon. I want to make that kilojoules. You could just change that, like move over 3 to the left would make it negative 21. You could do that too. I just stuck it in that way. And then that's per photon. You want to know per mole. And you're like, mole? Well, mole is a word for 6.02 times 10 to the 23rd of anything. So that's how many photons are in a mole of photons. So when you do that, you get that there are 399 kilojoules per mole in that photon. So does that photon have enough energy to break that bond? Yes, because it's greater. Yay! Alright, the next question, you only had to do part A, and the question is, what is the total number of valence electrons shown in the spectrum? So here's our electron configuration, right? 1s2, 2s2, 2p6, 3s2, 3p6. Valence electrons are the electrons in the outermost energy level. So people will get this wrong because they'll say 3. They'll look at the last one and they'll say 3, but you have to think about the fact that this is the highest energy level, has S and P electrons in it, so the answer was 5. Alright, now I had these in the wrong order from what I gave you, so back to here. Alright, so the above table shows the first 3 ionization energies. Notice that it's in the third period. So we are talking about elements in the third period. Third period. Alright, so 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 elements in the third period to begin with. So let's see. Element 1 has a pretty high, if you're looking comparatively, these are pretty high all the way across. Alright? So, what's the question say? Which one has the most, which one has, oh, we just hit my head on the camera. Alright, Which one has the most metallic character? So what's metallic character? Well, it's going to act most like a metal. How do metals act? Chemically. Like when we're talking about metallic character, how they react, how they act chemically. So metals react by losing electrons. So which are going to be the things that are going to be, if we look in this period, which one is going to be the most, well actually, I mean if we look at it, there's only 3 metals anyway. So which one is going to be the most likely to lose an electron? The biggest one is going to be the one that's most likely to lose an electron. So that would be sodium. And sodium has 1 valence electron. So if you look at what's going on here, I automatically look at this number 2 and I say, look, that's its first ionization energy. Removes 1 electron. Look at how much it went up. So this has got to be sodium. That's got to be sodium. Because once it's lost its first electron, it has that stable noble gas configuration. So to take another electron takes an act of God. Alright, so let's see. Is that what I wrote? I wrote it all down here. Alright, element 2, it has 1 valence electron. I know that because it has a significant jump in the first, in the ionization energy from the first to the second. The second is taking an electron from stable noble gas configuration, so it must be an alkali metal. Those have the highest metallic character because they have the biggest atoms, and they have the lowest electronegativity. So they're going to be the most likely to lose electrons. So sodium. It's element 2. Alright, what is element 3? So if we look at element 3, first ionization energy, kind of low. Second ionization energy, double, but still kind of low. And then the third energy level, wham, suddenly gets bigger. So it's got a +2 charge. That means it's got to be magnesium. You know, this concept is the one, this first, second, and third ionization energy, when I gave that test, that was, oh, you know what, you can't see what I'm doing because it's up here. When I gave that test, this is what a lot of people miss questions on. So you get this idea, first, in the first and the second, there's a huge jump. That means it's got a +1 charge. That means it's only got 1 valence electron. It's relatively small for the first, relatively small for the second, and then bam, it gets bigger. That means, you know, after you've lost the second electron, that's when you have the stable noble gas configuration. So when the magnesium loses its first, it loses its second, then it's got the stable neon configuration. Alright, so magnesium, because there is a big jump between the second and third ionization energies. So it must have 2 valence electrons. That's its electron configuration for magnesium. And again, we just said that this was sodium, so sodium's charge is +1. They're all in this group, so it has to be, that's the only one that's got a +1. It's got to be sodium. Alright. So, I'm showing you the answers. Alright. 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. That's nitrogen. Okay, now, I'm going to cover that up and I want you to see the answers. So you might be saying, hey Mo, what are you doing there? Half-life? What? I don't even remember what half-life is from. Half-life is from rates. Whew, that was a while ago. This is good. Did I expect you to remember this? Yes, because look, you have this. Did you look? When you're doing these, and I'm giving you them, because I have to give you, like, these are real ones. They mix ideas. Look. Remember this? Half-life is equal to 0.693 over K. What? All you have to do is say 10 is equal to 0.693 over K. And then you solve. And so again, because they want to trick you, like, you know, this has 2 sig figs. There is a point there. So your answer has to be 2 sig figs. So you make it 0.69 instead of, oh, you know what? I wrote that wrong. It's divided by 10. I did have we'll see, it's a good thing 0.069 because you're dividing it by 10. Yes. Now, what did you notice? Oh, so then it says, so many people got this wrong. Like, they got this part right. They got the 0.069. They got the unit wrong. Why? Because if you remember when we were doing rates, and we talked about rates, and I told you that they're obsessive about you getting the unit for K right. They are still obsessive about you getting the unit for K right. So first order, oh, wait a minute. No, okay. I forgot what I said in the last video. First order, it's 1 over second. Second order, it's liter times mole over second. Third order, liter squared over mole squared times second. Fourth order, liter cubed times mole cubed times second. You know, that pattern that we had. So all of it is always per second. But they gave us the half-life in minutes. And so the unit is not per second, the unit is per minute. And that's what, that year, a huge number of people got the question wrong because they didn't have the right unit. So again, you do have to put units in all your answers. But when they say include units in your answer, when they say that, that means they've done something tricky. That's what that means. We've done something tricky, so pay attention to what you're putting down. Alright, how do I know that this is a first order reaction? Because it's talking about it having a constant half-life. So if you remember, you might not remember this, but zero order and second order, the half-life is not constant. That's why when they're giving you this is only for a first order reaction. You don't do it with the other ones because it's not constant with the other ones. So if it has a constant half-life, it had to have been a first order reaction. So that's how you know it should be 1 over second, but since they gave us minute, it's 1 over minutes. We should pray for these AP people. Let's pray. Let's pray. In the Father, Son, Holy Spirit, amen. Dear Saint Joseph of Cupertino, please, Saint Joseph, please have them only put questions that my folks, us, we all know the answers to. Make it be on something that everybody really understood. Lord of Saint Joseph, go to the Lord and tell him that this is what we need. We want only there to be questions that my folks know the answers to. That would be glorious. Amen. In the Father, Son, Holy Spirit, amen. Saint Joseph Cupertino. Who's the other one? Saint Albert. Saint Albert is the patron saint of chemistry students. So we need to be praying to both these people. We want FRQs we know all the answers to. Yes. All right. Then the next one says we have 64 atoms originally. When we're done, we have 1 atom. 64 to 1. What's the expected amount of time? Now, truthfully, you can use its first order. So which one is first order? This is first order. You can use this equation, but you don't have to. It is much easier to just say, okay, 64 to 1. How many times did that cut in half? Alright, 64 divided by 2 is 32, divided by 2 is 16, divided by 2 is 8, divided by 2 is 4, divided by 2 is 2, divided by 2 is 1. How many times did I cut in half? And this is an okay answer. 6 times. So 6 times 10 is 60 minutes. Alright, this better save, or you're going to hear me screaming. You're going to be like, what was that noise I just heard? It was me screaming. I love you all. See ya.